So now another way of looking at how well will a mechanism operate is mechanical advantage. And where we use this is for mechanisms that are used to amplify force or motion. We want to know what is the ratio of that amplification. This is described by the mechanical advantage of the mechanism. So I've got here a vice grip pliers, and this happens to be a mechanism that amplifies quite a bit of force from the input to the output, and we'll be using this as an example of analyzing the mechanical advantage. So first of all, the mechanical advantage is defined simply as the output force divided by the input force. So in this case, my output force would be the force that's being applied to the jaw. The input force is the force that I am applying to the handle of the pliers. Now, the way we start with this is we start with a conservation of power. And if I assume that all of my joints here have relatively low friction, which is a reasonable assumption for many mechanisms, I can then say whatever power goes into it is the same as the power goes out of it, and then I can start doing a power balance from there. So let me first of all start here and say my power in a rotational mechanical system is torque times angular velocity. So power here is torque in times angular velocity in, and then that's equal to torque out times the angular velocity out. Now I can do a little bit of rearranging with this and say, well, a torque is just a force times a distance. So I can say I've got a force in, a radius that I'm acting on in, and then the angular velocity, and then the same thing on the output side, F out, R out, and omega out. And now I've got these two forces. I know that if I divide the output force divided by the input force, that is my mechanical advantage, and then I just simply rearrange these radiuses and these angular velocities. So I can put this in terms of mechanical advantage is the output force F out divided by F in, and then this is R in times omega in divided by R out and omega out. So we're almost all the way there, except now I have a little bit of a challenge. Well, first of all, I have these radiuses that I need to measure, and I need to know where am I going to measure them to. And for this mechanism here, the output being the jaw that's pivoting on ground. So let me first of all say that this jaw right here, the lower jaw, is pivoting on that point right there. And that is where we're going to measure our radius from. But the link here, this coupler link, link 3, which is actually where I'm applying the force on my handle, where do I measure this force back to? Do I measure it back to this pivot with respect to link 3? Do I measure it back to this pivot with respect to link 2? Happens to be that neither one of those is right. So we need a little bit more to help us. Also, I have this angular velocity ratio, this angular velocity of the input relative to the output. How do I deal with that? Well, one tool that we're going to use to get there is instance centers. And these are instance centers of velocity and very commonly used in velocity analysis. So we're going to do a very quick crash course in instance centers, hopefully a review from what you've seen in your undergraduate kinematics course. So I've got this same mechanism, and now I want to look at the instance centers of this mechanism. And I've got all of my links labeled, and I've got the mechanical advantage again over here on the right side. And the only thing that I've substituted in here is omega 3 is the input link, and omega 4 is the output link. Everything else is the same. So let me first of all work on getting this velocity ratio between the two. So instance centers. Starting off, instance centers are just a point where two bodies have the same instantaneous velocity. So some of the easiest ones to find are saying, all right, I recognize that link 4 pivots on this point right here, which is link 1, and I can label that as instance center 1, 4. Similarly, I have links 2 and 3 pivoting right there, 2, 3. And we know that a pivot, those two links have to share the same velocity because that pivot point is being shared by the two links. And then, hard to see, but inside of this pliers, I've got this link 3 right here, link 2, and it actually has a point right here that then pivots inside the pliers on the end of the screw, and that would then be somewhere right around here, and that's instance center 1, 2. So I've got then these 4 instance centers, this would be 3, 4, that are quite easy to find. They're where two bodies have the same instantaneous velocity. Now, how do I find additional instance centers? What I can do is I can use Kennedy's rule, which tells us that 3 bodies have 3 instance centers that lie along a line. So if I happen to have 2 of the instance centers, I can then find a third one, which will be along that line. And if I have 2 intersecting lines, now I can find where specifically is that instance center located. So what I'm going to try to find here is instance center 1, 3. Instance center between link 3 right here that I'm going to apply my force at and ground. So the way I'll do that is with what we call a bookkeeping circle. So I'll create a circle here, and I'm simply going to put the numbers on this for however many links I have, 1, 2, 3, and 4. And then I will put lines on here for the instance centers that I already have. So I have instance center 1, 4, as well as 1, 2. Those are both the instance centers on the top handle of the pliers, which I'm calling ground. I've got instance centers 2, 3, and 3, 4. Those are my two moving pivots, if you will. And now if I want to find instance center 1, 3, I go vertically through my bookkeeping circle. And so I know that 1, 3 will be along a line that is 1, 2, and 2, 3. So I have 1, 2, and 2, 3. So if I extend this out, I've got a line that is lying something like that. And then I'm also going to have, bounding this with Kennedy's rule, 1, 4, and 3, 4. So I have 1, 4 up here, 3, 4 right here. I extend that out, and I find that both of these intersect at this point right here, which happens to be instance center 1, 3. So now that's how I can find instance center 1, 3. If I was interested, I could also do the same for 2, 4 and find that 2, 4 was along a line from 1, 2, 2, 4, 1, 2, and also 1, 4, so along the axis of the plier, as well as 2, 3, and 3, 4. So if I wanted to find that one, I could do that one as well. It's going to turn out that I'm not going to need it. So how do I find these velocity ratios? Well, remember that these instance centers are locations where bodies have the same velocity. So instance center 1, 3, this is the location where link 3 has the same velocity as ground, or we could think about it for this one instant at a time as purely pivoting about ground. So I can then write an equation that says the angular velocity of link 3 times its distance from its instance center with respect to ground, 1, 3, to the common instance center with link 4, 3, 4. So this distance here, so what I'm looking at is the distance from 1, 3, this instance center that I just found, to instance center 3, 4, this distance right here. I'm multiplying that by the angular velocity of link 3. And then I can say that that is equal to the angular velocity of link 4 times the distance from its instance center with respect to ground, 1, 4, to that same common instance center, 3, 4. And again, that's a distance, 1, 4 to 3, 4. I can simply measure it off of my drawing here. Now, why did I want this? Well, you'll notice that over in this mechanical advantage expression, I've got omega 3 divided by omega 4. Well, I can now create that expression here from my instance centers. So I can say omega 3 divided by omega 4 is equal to the distance from 1, 4 to the common instance center 3, 4 divided by the distance from instance center 1, 3 to instance center 3, 4. So I've got that angular velocity ratio. So I can simply measure those distances, and I then have enough information to get that velocity ratio. Now I just need to get these radiuses that I'm applying all of these forces at. So let me switch colors here and grab a different color. And now I'm going to measure these distances. Every time that you're doing a mechanical advantage analysis, you always have to measure the distance back to the instance center of that link with respect to ground. So in the case where I have link 4, I'm going to measure it back to 1, 4. So let's say I have a force being applied right here. This will be my output force, F out. I'm going to measure that back perpendicular. So this will be perpendicular to that force. This right here will be my radius out. Similarly, for my input force, let's say I'm grabbing onto this and applying a force right here. That's my input force. That's what I'm doing with the handle. That input force on link 3 has to be measured back to instance center 1, 3, the instance center of link 3 with respect to ground. So 1, 3 was right here. I need to, again, make this perpendicular. So this distance right here, this is perpendicular to the force. That is my radius in. So now I have enough information. I've got these two distances, the two radiuses that I can measure right off the drawing. And then I've got the two distances in terms of the distance between the instance centers. I put all this together, and I have my expression for the mechanical advantage purely with respect to the static analysis of the mechanism. I can measure all of these and get this information quite quickly. So pretty powerful in what we can do with an instance center analysis. We've talked about it for a pin-jointed mechanism. How about for a slider? Here I happen to have a mechanism that is supposed to be a can crusher. So imagine I'm grabbing link 2 there, I'm applying a force to it, it then has the coupler link, and then link 4 is going to slide and crush this can of Coke. That's the objective of the mechanism. I'm going to have an input force right here, F in. I'll have my output force, which is the can. Let me extend that out a little bit, F out. And I want to do a mechanical advantage of this. Now remember our mechanical advantage analysis that we just looked at, we had an angular velocity ratio. And if I worked this out, I would go, wait a minute, I'm doing an angular velocity of link 4. This is a slider on ground. Sliders have no angular velocity. They don't rotate. So what do? Do I punt or do I reformulate? How do I start with this? What we're going to do is we are going to reformulate our mechanical advantage analysis, or the formulation of it, just to help us out with this slider condition. So again, I'm going to start with a power balance. Power in is equal to power out. Now my power in can still be a torque times an angular velocity, and again a torque is a force in times a radius in times an angular velocity in. And then my power out, I'm going to keep this in the linear mechanical, so just a force times a velocity. So I'll have a force out times a velocity out, so in this case velocity of link 4. And now I can express my mechanical advantage, MA. This is just equal to the output force, F out, divided by F in, which is then, let's see, throw these to the other side. I get, make sure I do this correctly, R in, omega in, over velocity of 4. All right, so I'm getting pretty close now. My input link is link 2, so I could substitute omega 2 for omega in. And I know that link 2 is pivoting on ground, so I can very quickly say I know I'm going to measure that with respect to instant center 1, 2. So this is my radius in. So that's pretty easy. But now I need this velocity ratio between omega of link 2 and the linear velocity of link 4. So again, I can use my mechanical advantage analysis here, and I can say that links 2 and 4 have the same velocity at instant center 2, 4. So I will use that to my advantage here. So let me just write that out. So links 2 and 4 have the same velocity at instant center 2, 4. At IC 2, 4. All right, so I can say velocity of 4 is just equal to omega 2 times its distance from instant center 1, 2 to this common instant center 2, 4. All right, so I've already found 1, 2. How about 2, 4? I don't have that one yet. So let me flip over to a different color and let's find our instant centers for this mechanism. Again, I can find 1, 2. I've done that. This point right here is instant center 2, 3. I've got instant center 3, 4 right here. Now the other link that is sliding with respect to ground is link 4. And so I'm going to be looking for instant center 1, 4. And because link 4 is a slider, it's equivalent to an extremely long pinned link. So I could say that the instant center of link 4 is vertically, either up or down, an extremely long distance. So my instant center 1, 4 is at infinity in either the upwards or the downwards direction. You could think about putting a pivot way, way, way up here, which then has an infinitely long link coming back down to link 4, and that would be the equivalent mechanism. So I'm saying the instant center 1, 4 is that far away. Again, I create my bookkeeping circle because I want to find 2, 4. So I've got link 1, link 2, link 3, and link 4. The instant centers that I've found so far are 1, 2, 1, 4. Those are both of the ones for the links that are on ground. I've got 2, 3, and 3, 4. And so I want to go across my circle here to 2, 4. And so I know that it lies along a line from 2, 3 to 3, 4. So 2, 3, 3, 4, that is the coupler link. So I'll extend that line out, something like that. And then it also lies along the line of 1, 2, and 1, 4. 1, 2 is the ground pivot of the input link. 1, 4 I said was at an infinite distance. So if I draw a line from 1, 2, an infinite distance to that instant center 1, 4, it would be a line like that. So this is parallel to this guy here. I then say, all right, Kennedy's rule tells me that I've got 3 instant centers along each one of these lines. They intersect, so this location of intersection is instant center 2, 4. And now I can measure the distance from 1, 2 to 2, 4. That's this distance right here. And I can simply plug that into this velocity ratio, and I have enough then to calculate my mechanical advantage for this slider mechanism. So again, mechanical advantage is quite useful for many mechanisms. It can be applied to the 4 bars we talked about here, whether pinned or sliders. It can also be applied to 6 bars, 8 bars. We can just keep going with this. And the instant center method is a very convenient way of graphically looking at what is the mechanical advantage of a mechanism, telling us what's the force amplification, or we could think about it as a velocity amplification if we prefer. So really is a quick way of determining how well will a mechanism operate.